Swayam Prabha. Digital India. Educated India.
Hi, welcome back. So, what we were looking at, so we've looked at this a plane jet, okay, and with respect to this, we've also had the lateral velocity, right? The lateral velocity, which is v, okay, u naught is essentially the, so u naught here is the centerline velocity, v is the lateral velocity. What we mean by lateral velocity is basically in here, if you see the y direction, so this direction is the direction of the flow, right, the free stream velocity. So this is the direction of flow of the jet, okay, and a direction perpendicular, a direction normal to that, perpendicular to that, is what is being called as the lateral velocity. Now, I think we've discussed this earlier, etc., that this is very small, which probably it is, okay, but we just plot that and let's see what it looks like, okay. So if you see here, okay, let's just look at the plots a little bit. So we've got this is the y by delta, okay. This distance that you see is basically y by delta. So yeah, so this y is again the direction which is perpendicular to the flow direction of the jet, right, and delta is the jet half in the jet half width, okay. So y by delta is equal to 1 is here, right, and you can see that all these three curves that we have here kind of merge with each other, and there seems to be a change. Okay, we'll look at that. So if you see till y by delta is equal to 1, if you look at this part of the curve till about 1, what you see is, so okay, before I say that, so there's a dotted line, okay, that's the dotted line, and there is the line which is has the circle markers and the other one which has cross markers, okay. Now the dotted one, the circle, the circle markers are x by h is equal to 20. So we are looking at a distance away from, so we are looking at a distance away from the nose, say, okay. So this is the h, and this is the h, okay, and this is the direction, right, x direction, as you can see, and 20 times h, so 20 times this width, I guess, of the paddle plates. So that 20 times from here, okay, so that is 20 times here and 60 times from there. So basically two locations on the x-axis, and we are looking at the lateral velocity. So at two locations we are looking at how the velocities vary in the y direction. That's what we're doing here. That's what the plot is all about, okay. So in this case, so these are the two, so at two locations, okay, and u1 by uj is basically the jet velocity, of course, yeah, and u1 is the free stream. So as you can see that u1 is 0.16 times the jet velocity, okay. This is v by u, okay. So and the dotted line, actually u1 is actually equal to 0. So we actually do not have a velocity in the x direction, okay. So in that case, how does but there is a v velocity though, okay, and so that is a kind of a baseline case, and we have, so that's that, and then you have the delta dx is equal to 0.1, okay, the slope of this, okay. Now, so now if you see till about y by delta till about 1, right, if you see till about 1, okay, let's just say till about this this point. Okay, so if you see the essentially, you know, you have the u1 is equal to 0 case, okay, right, that has the highest v value, and then next you have the x by h, and then you have the x by h equal to 60. Okay, so as you go further down the x-axis, as you go further down the direction of flow, the v velocity seems to be decreasing, right? That's what it looks, if you look at the plot, that's what it looks like. Okay, so you can take you know, so this is like the maximum around, this is the, you know, around the maxima. So as you can see, as you gradually move, and you can draw one another, you know, location here, right, as we move along the x-axis, right, as we move along, this is the, as we move away from this distance or height, you know, as we move away from the jet center line. Okay, so the y velocities actually, so the v velocity rather, the v velocity, right, that decreases, right, that decreases. And now after y by delta is equal to 1, so this is the place, this is the location where it's just jet half fill, and after that you see that actually the curves are actually reversed, right. So and then at a certain distance, all of these things, you know, all of these curves, you know, become negative, right? All of these curves are becoming negative. Okay, so for example, at a distance 1.5, okay, which is y is 1.5 times the jet half width. So if you go there, you see, okay, so the minima, the negative minima is that of u1 is equal to 0 case. Okay, then you have the circle markers, and then you have the cross markers. Okay, so as you increase the distance, as you increase the distance in the x along the flow direction, which is the x direction, right? So this is x by, it is 20, this is x by 60. So further down the direction of flow, the negative velocity actually, see negative lateral velocity, yeah, actually decreases. Okay, okay. So we've looked at that, right? So essentially, so let us kind of jot this down. Okay, let us jot this down and write out these inferences, what we are seeing, you know, and what is this telling us about, you know, the flow of the, what is this lateral velocity actually telling us regarding the yeah, the flow actually. Okay, so well, the example was simple. So example was essentially, we said explain figure 1c, that's all. Okay, that's what we said, just explain figure 1c. Okay, okay. Now I think I want to discuss, but I'm going to write this down. Okay, so essentially this is a figure, so this is it is showing, this figure is showing, you know, the y component of velocity in a plane jet. Okay, now so okay, free stream, this is equal to 1/6. Okay, so which essentially, this essentially means that free stream is equal to 0.16 times the jet velocity. Right, these are some things that we've right. So there are well, 3 conditions actually. So 3 cases that's been considered. Okay, so number one is shown with circle markers. Okay, this is okay, that is distance from the parallel plates distance from the parallel plates along the flow direction, right? Okay. The next one is markers, is cross, and this is slightly further down, right? Further down. And there is also a third case, right, which is shown by dotted lines, right? It is a quiescent condition. Right? That is, yeah, so essentially quiescent condition, that is u infinity is equal to 0, right? Okay, and delta of course is the jet half width. Okay, all right. So now let me. So I'm going to I'm just looking at the. We just looked at the plots, and I just want to, draw a few things from there. Okay, so let's just move to another page here. Okay, let's just say, okay, now I'm going to just draw it a little like this. Okay, this will be the velocity. Okay, so u naught is the this thing. So let us say we're going to take three locations. Okay, so let us take three locations. Okay, so here this is the quiescent condition. Okay, this is, and this is marked with circles, I think, right? And further down, and this is marked with, yes, the 60H is marked with cross markers. Okay. Now, if you see here, so now I have this location here. Okay, let's just say this, this height here, right? So this is y by delta is equal to 1. So this, this location is actually basically the jet half width. Okay, and u naught, of course, is the centerline velocity. Okay, now u naught, of course, is the centerline velocity. Okay, now if you look at this plot, if you look at this plot, okay, you have something like this. Okay, so what you have here is this. You need to scrutinize the plots, right? So you reach a maximum, right, and then it keeps moving. Okay, so this is the location where the it reaches the y is equal delta is equal to 1, right, and then right. So these this line is essentially v is equal to 0. Okay, so this here v is equal to 0, or let's just say rather this line here, v by u naught is equal to 0. Okay, so this line, so I'm going to just draw as that, so v by u naught is equal to 0. Okay. Okay, so this line here, and then this is the velocity that you're looking at. Okay, now here this value, okay, now this value, okay, these are values that I'm getting from the plot, so you should be able to look at that. It's 0.2, so this is your v value actually. So v is equal to 0.02 that. Okay, and when you come here, this is here is v is equal to 0.01 this thing. Okay, this, and when you come here, this is 1. Okay, now this is, you can see here, okay, this location. Okay, so here v is equal to 0. Okay, v is equal to 0, and this location here, okay, so y by delta is just a little away from the jet half width. Okay, and so what we're looking at here is, this is the v velocity. Okay, so the v velocity is so as we move along, so it's increasing, right? So it's as I go along y, so this is my v velocity, so this increases until here it reaches a maxima, which is 0.02, right? And then it starts dropping down, and at the jet half width, okay, it's almost half of what it was here, the maximum. It continues, and then it continues to decrease, and then it reaches 0 at about 1.1 times the, a little just over just outside of the jet half width, and then it starts decreasing. The v velocity is decreasing. Okay, so that's what we see for the quiescent, and this is a plot with the values, etc. Everything is something that I'm getting from what is plotted there. Okay, now we come to the, as we go further down the flow direction, so we come to x is equal to 20h. Okay, so when I go there, okay, so what I see here is that now what we see is, okay, so here it increases, and okay, now here, so this one, okay, this here v is actually equal to 0.018 of the free stream. This is the maxima. Okay, and this one, okay, is actually at the jet half width, it's still this, right, and this is the location at which it is changing direction, and this here is (1.25), right? So here the wide, it's a little away from the jet half width. It's about 1.25. So what we see is, as we go down the flow direction, okay, the maximum y velocity has decreased, as you can see, right? So it has a higher change in slope, and then the distance at which it crosses, it changes sign, is also slightly higher. Okay, it's slightly away from the center line. Okay, so which is 1.25, and if I go further down, we see a repeat of that. Okay, so let's just say here. Okay, so before I do that, so this one is actually with these markers. I'm just these markers are not placed exactly as in the plot. This is just for my reference. Okay, this is the plot, and here again, so for the x is equal to 60 case. Okay, so you okay. This. Okay, and here this is all markers are with cross. So here this one, right, the maximum velocity, okay, this again decreases, which is 0.016. Okay, this, and again here the location where at the jet halfway this is also decreasing actually. Okay, and this again height is slightly further up. Okay, so this here y by delta is 1.35. So this is where it changes sign, right, and this is okay. So so what we see is, so that this is basically you know, just trying to explain the plot that we just saw and what we're trying to understand. Okay, so I think we've of course spoken about this earlier on, and and you can see that, you know, the lateral velocity, which is v, right, this is v, so it changes sign, right, it changes sign at a certain y location. That y location is near the jet half width. Okay, and it is so as we go down the x-axis in the direction of flow, right, so because the spread is higher, delta is, you know, larger. So what we see here is that so what essentially we see is that the velocity is you know, goes slightly beyond that distance, which is the jet half width. Okay, so that's where it changes sign. Okay, so it reaches a maximum and then it decreases. Okay, and it changes sign as we and it reaches a maximum before reaching the jet half width. So around the jet half width, okay, it's nearly zero, but not exactly. It's a little you know, around that jet half width, which is, you know, if it's quiescent, then it's about 1.1 times the jet half width is 1.25 and 1.35 as we go further down. So I think as we go further down, the spread of course of the jet is much more, right, and therefore the location at which the lateral velocity changes sign is a little further away. It increases, actually the distance increases at which it changes sign. I think that's what we're trying to get at. Okay, so it does. Now this whole change of sign means what, right? The velocity is now basically flowing into the fluid, right, which is entrainment. So this change of sign here, okay, so when you have this sort of so this is the change. Well, this is basically the change of sign. Okay, so this is, here is the sign. So this is change of sign. So this change of sign actually, right, so change of sign, well, we know this, right, so essentially that means direction of v is reversed, right, that is, it is flowing into the jet. Right? I think we've discussed this earlier. So it's flowing into the jet. So, and this is essentially called, so, and this is called entrainment, right? Okay. Well, essentially that. Okay. So now when I look at the plot, so basically this is what I'm able to gather. This is all the information I'm able to gather. Okay. The only thing is that the v velocity is much smaller compared to the x component of velocity u. Okay. And therefore we tend to sort of ignore that. But this is also giving us physical behavior, information about the physical behavior of the flow in the jet, and this is what it sort of looks like. Okay, so going back just to the plot here itself, so this is what we were looking at. So you can sort of scrutinize this. Right, scrutinize this and look at some of the values that I have written here, okay, and check for yourself. Okay, yeah. So the distances, the y distance, I've kind of just about made a reconnaissance, and they're not exactly. I'm just trying to understand what these plots mean, okay, what these plots mean, and as I go further down, the flow, what does it, look like, okay. All right, so I think, so that was figure 1C, okay. All right, so I think having done that, let's look at something else, okay. So that's that really, okay. So we will look at another example. Okay, this is again for jet flow. Okay. The extraction momentum conservation equation right, for a jet, right, that looks like this. Okay. Turbulent this okay, so this is the numerical equation, right, extraction momentum conservation equation. Okay. Now the question is, explain how the above equation does or does not behave in the following cases. Okay. Jet flow near solid walls, the jet flow near the solid walls, okay, and jet flow away from the solid walls. Yeah, I think we've discussed this earlier. I'm just trying to, put this in a sort of a question answer kind of a mode. Okay, so we have this x direction momentum conservation equation, and we're trying to see how this equation will behave, because this is a numerical equation, right? And if you are near the solid walls, how will this, what sort of changes should come in here, okay? And if you go away from the solid walls, then how will the equation look like? Okay, so now, jet flow near solid walls. Okay, now jet flow near solid walls. Well, here all the terms will dominate. There's nothing that I can take out of here. Okay, when it's near the solid walls, everything will dominate. So you have essentially the mean component of the mean x component of the velocity, right? And then you have the turbulent quantities, u dash and v dash, right? And depending on how the free stream pressure behaves. Okay, so all the terms will dominate. Right? Now, jet flow away from the solid walls. Okay, how does that change? Okay, well, here there are essentially two changes. Okay, now this term, the first term, okay, is a new. So the first term here. Okay, so new. Okay, so this is of the order right. So nu u by delta square, and this is of the order of that. Okay, or in free shear turbulent flows, right? Now, so essentially, now what I'm trying to say here is, so if that's the case, now this is of the order this, which is 1 by Re. Actually, let's just say right, this term on the right hand side, the first term on the right hand side, yeah, is of the order 1 by Re, right? Now, in free shear turbulent flows, right, in free shear turbulent flows at high Re, this then becomes so that is to say, if it is 1 by Re, so if you have very large Reynolds numbers, then it's going to become insignificant. So the first term here, okay, that will become very insignificant if you are operating at very high Reynolds numbers. So essentially, in free shear turbulent flows at high Reynolds numbers, this becomes insignificant, and we can sort of get rid of that. Okay. So then, then the next thing is this term, the third term actually. Okay, so this is the term that you're looking at now. Okay, now this is a term. So what we are looking at is okay. So this one, well, it accounts this term. It accounts for 10% of the term of the dominant terms. Okay, so which essentially means that can be neglected. Well, this is basically to say that when you are sort of far away, right, from the solid walls, okay. So the third term here, here, it is actually quite small compared to the other terms, right. So, and it can be neglected. So, it's not 0, right, and this is so. However, if you are far away from the solid walls, right, and so this term is actually quite small compared to the other dominant terms, and therefore it can be neglected. Okay. The other thing is, see, all viscous terms are negligible anyways. All viscous terms negligible away from the walls. Okay. So I think that again sort of, so anyway, that all viscous terms from the walls. All right. So sort of to now just wrap this up, I'm going to just write out these equations. So basically that's all to say, so you have this in the sense that, you have this equation which kind of looks menacing, okay, but you can have, if you're sort of, you need to have an idea, because we just spoke about this one, we are looking at this sort of a thing, and you see how the lateral velocity is behaving. Okay. So, how lateral velocity is behaving as I move down the down the direction of flow and in the direction of the spread of the jet. So, the velocity is changing, the velocity is decreasing or increasing or changing sign and doing lots of things, right. Now, this is something, this is an experimental result. Now, this should reflect in your equations as well. Right. Now, what if you look at around a distance, for example, say look here. So, if you are about this distance away from the center line, which is slightly away for say the quiescent condition, right. So, if you are looking at this plot, so the v velocity is anyway 0. Right, the free velocity is anyway 0. If you are here, although again, I'm talking about the v velocity here, sure, but then this is going to come into the equations. Okay, now this velocity overall we neglect this because it is small compared to the lateral the flow direction velocity, u velocity. But even if we were to, not to do that, what you see is that the v velocity actually, right, if you see, it's near about the the jet half width, it is very small, and it is actually 0 about that, about the v velocity becoming 0 around this area. Okay, now this is going to reflect in your numerical equation, right? This is going to reflect in your numerical equation, in the sense that if if you are operating somewhere, if you are looking at the in equation somewhere around here, the v has a little more dominance than if you were to operate around a little more farther away from the center line. Okay, so similarly, so that's the kind of question we kind of posed here, that this is the numerical equation, right, and I am near the solid walls and I'm away from the solid walls, right. So what does it do to my equations, right? This is a numerical equation, right, and all of these, what each term is doing is trying to simulate an actual physical phenomena, right. And we've seen several examples that the velocity that we are trying to calculate or get a measure of, right. So I'm doing that by experiment, and if I'm using these equations, right, now they have a distribution, it's not linear, right. How does it behave? Right? It is changing signs, it is changing slopes, it's doing all sorts of things, especially if you see in a turbulence case it becomes complicated. Even so, if you go down in a flow direction, if you go down the flow direction, okay, even the slopes are different. Right? When I say it is increasing, yes, but then at different locations even the slopes are different. Okay. and the location at which you know, it is changing sign is also different. Yeah, they're all small enough, but then it's different. Okay, so it makes sense to kind of look at this equation and trying to figure out that how this thing is going to behave. You know, how is this going to behave when, you know, for in this case I'm looking at jet flow near the solid walls or away from the solid walls. So so if I'm near the solid walls, okay, everything, I cannot take out anything. Okay, everything is in a dominant. Okay, but if I'm away, so if I am at a higher, you know, if I'm operating at very high Reynolds numbers, you know, so then this first term, okay, it actually varies. It's is of the order 1 by RE. Okay, so if you are in a very high Reynolds number flow, then it becomes insignificant. So then you can you know, remove this term. Okay, so in that case, so if you have that information, now that you have that information, if you are going to work in a turbulent flow at very high Reynolds number, so you can get rid of this term. You know, you don't include that. You know, so you have a little bit of relief in terms of how many calculations you have to make. Your equation becomes a little more simplified. Okay. Another thing is that this term here, the third one, right, when you are away, so when you are away from the you know, in walls, so that also can be neglected, but because it is considerably smaller than the other dominant terms. Right. So now the thing is, for example, when you write out your numerical equations, you are developing your numerical code. So you know, you have to define now what is far away. What is far away from the you know, away from the solid walls. Now, if you can define a certain distance, you know, according to you, so then you say, okay, when you are inside, you know, this distance, then you solve this equation. Okay, the full equation. When you're away from it, then you solve a simpler equation. Now, this is typically what we do, right? In a boundary layer flow, for example, right? So we say that when you are near the you know, the plate, right? When you're near the plate, so then you need to solve, you know, complete viscous Navier-Stokes equations. But if you're certainly away from the inner plate, how away is that, right? That is the delta. Now that you have to define. Right? So in your computer code, once you can define it, then you say, okay, once you are about that distance, then you can use you know, the potential flow equation. Okay, that will suffice, you know, because the viscous terms become negligible, which is again what I've written. All viscous terms become negligible away from the walls. Right. So in that, just to remind ourselves, I'm going to just write down, right, the boundary layer equations, you know, and how they look like. Okay, so for statistically 2D, okay, I write this properly. I don't know what I wrote. Okay, that's better. 2D, okay, stationary flows. Okay, bounded by quiescent or uniform free stream. The turbulent boundary layer equations obtained by, you know, applying suitable assumptions. I think it is this whole concept of Prandtl, this concept was introduced by Prandtl, where you said that when you're near the wall, when you're near the plate, near the wall, that's where the viscous terms dominate, and when you're away from it, the viscous terms don't dominate. So this whole concept that I can actually use two different numerical equations, in my flow field was something that Prandtl introduced, and I think that's where we're coming from here. We kind of trying to use that, and therefore we talked about how a turbulent jet has actually similarity between a boundary layer. I think, and we've done we've talked about that, and we've done some examples on that as well, right? And we said, what is the significance of delta? So this is, that delta, as we saw, that it increases, the height it actually increases as we go in the flow direction, and this is kind of similar to a laminar boundary layer thickness as we go down the flow direction. So I think that's where we're coming from. Okay. All right. So these are the equations. These are my typical boundary layer equation. That is my continuity. Right, that is the x momentum equation. Right, this is the y momentum equation. So as you can see, so this is your continuity, right? This is your x momentum, and this is your y momentum. So you can see when I say by applying suitable assumptions, what do I mean by that? What I mean by that is that when I do the y momentum, I've already assumed that here, I've already assumed that this is much smaller than the lateral velocities, right? And that's how we come up with this, right? And so similarly in the x momentum equation also, you can see that we've made assumptions. Okay, so this whole concept that when a boundary layer equation, this is something that I'm applying. These are equations, boundary layer equations. So these boundary layer equations are essentially the same old Navier-Stokes equation. I mean, I'm talking about a laminar boundary layer, but then I apply it to near the boundary. Okay, and when I do I have even a course on boundary layer theory, or you can consult a book and you can see you start boundary layer equations, nothing but you start from the same old Navier-Stokes equations, but you go down and sort of bring changes to it so that it's suitable to work. And you have to know that in a boundary layer, one of the more important things is the length scales, because the y scale becomes much smaller than the x scale. Right. So if you want those terms in the y direction, to mean something, then you need to bring that y scale down. That scale to matter. Otherwise, if you have the entire, a single scale for the entire, equation, these things will actually going to fade out. Then it doesn't give you the viscous nature of the flow near the walls. Okay, so that's how you get the boundary layer equations, and so this is the equation that I've written out here is the same Navier-Stokes equations. Okay, this is for a turbulent case, and we've seen this earlier. So we bring in the similarity, the similarity with the boundary layer equations, and this is what we came up with, and this is how those equations look like. Okay. All right, so we will stop here, and we'll do a couple of interesting things after this, and take it from there. Okay. All right, so I will stop and see you in the next class. Okay, thank you.